Okay, welcome to another lecture of CS 159, Data-Driven Algorithm Design. Today we'll have my PhD student Jialin Song give a lecture. Jialin's thesis work is on using reinforcement learning and imitation learning methods for learning to optimize in discrete optimization spaces, which is what he'll be talking about today. Take it away, Jialin.
Okay, thanks, Susan. So good morning, everyone. So I'm happy to be here to share with you some of my thesis research. I'll use different policy learning methods for learning to optimize problems. So let's get right into this. I don't think I need to stress anymore now that optimization is a core component in many of the practical applications. And the traditional algorithmic approaches for a lot of optimization problems, they tend to tailor to specific problem structures. So here I'm just listing a few examples you are probably familiar with. For example, in linear programming problems, simplex methods are designed to take advantage of the structure in terms of the linear constraints and the linear polytope facets to iterate to find the optimal solution to a linear program. And so the class of problem called monotone submodular optimization problems, the greedy algorithms, which is a very simple algorithm, but takes advantage of the submodularity of optimization problems that can give fast and theoretically guaranteed learning outcome of optimizing this class of functions. And finally, which will be a main class of topic for this lecture, is integer linear program. So for this class of problem, people have designed branch and bound, which is a general tree search algorithm, which I'll go into detail later, to learn how to find the optimal solution to this integer programs. And here the tree search structure is tailored to the problem structure because they are discrete for integers. So that's why we can formulate the search problem as navigating a combinatorial search tree space. And so the research question of my thesis research and also covers this lecture is, can we do a data-driven approach to effectively learn optimizers from data for problem instances generated from specific applications? So the framework we'll be using in this line of research is sequential decision making. So this is a very general problem formulation where I need to make a sequence of decisions to arrive at some solutions or some objectives. And specifically for the optimization problems, we can view many of the optimization procedure as sequential decision making. So for example, in gradient descent, we're operating sequentially updating the parameters, say for a neural network by following the gradients. And we're doing this in an iterative fashion, doing this one step at a time. And for branch and bound, as I mentioned before, this is a tree search structure. So we'll sequentially build up the tree to find where the optimal solutions are. So this is a sequential nature. So in general, sequential decision-making encompasses a class of problems where the future decisions depend on the current state. And for some instances, the reward or the result of a sequence of actions may only be revealed in the end. And so for this lecture, we'll be using two classes of policy learning for the sequential decision-making procedure. So one is imitation learning. So this is a class of learning method that's inspired by how humans learn. So we tend to learn from imitation. Given some demonstrations, we can extract information on how to behave to match the behavior we see in the demonstrations. And the second class is reinforcement learning. And so this is more without existing demonstrations, and we'll learn by interacting with the environment and get the feedback through the reward and update our behavior accordingly. So I just go through quickly some related works in this learning to optimize domain. So this will be a very tiny slice of the materials we cover for this class, and some of which has already been covered in previous lectures. So the first class is the discrete and combinatorial optimization problems. So this are problems involving discrete decisions I can make. For example, how to generate a schedule or how to allocate some resources. And so specific in this case, there are two work I think are representative. So He et al. So that's the learn to search in branch and bound algorithms. So here they learn this node selection policy in this branch and bound tree search framework for solving integer programs. And the other class of problem, the other work focus on learning general graph combinatorial optimization problems. So for example, maximum cut and minimal vertex cover. They learn the greedy policy characterized with a deep Q learning model to do this graph optimization procedure. And the second class is on continuous optimization. So we mentioned the gradient descent procedure, which we can think of as this sequential decision making. And so there existing work on, for example, and Drogwitz and learning this parameter, how to update this gradient, given a gradient, how to update the parameter. And I believe Joe Moreno also in previous lecture talk about his amortized inference models for doing continuous speed up continuous optimization. And finally, so Yisong has covered this a lot in terms of algorithm configuration. So that's the class of work where we have some existing algorithms, but they're parameterized by some very important parameters that will affect the performance of the solver or algorithm greatly. And this class of methods aim to tune this parameter so that we can optimally, effectively leverage the existing solver to be effective on different problem instances. So for this lecture, I'll focus on discrete optimization and show with two works I have done on how to apply different policy learning methods to speed up the optimization procedures. So the first one we'll cover is called learning to search via retrospective imitation. And so here we seek to provide theoretical characterizations for this new learning algorithms. And it's based on imitation learning. And the second work we'll cover is called co-training for policy learning. And so here we're designing a principled way to combine different learning paradigms. And so as the name suggests, we'll combine reinforcement learning and imitation learning and blend them together into this one unified framework to do policy learning for discrete optimizations. And so firstly, I'll go into the first work, and there's a joint work with Ravi, Albert, Adia, Yisong, and Hero. So before I start, I just want to frame this learning to optimize as a pipeline. So so just like supervised learning, we have this training, validation, and testing pipeline. So here we also have a similar pipeline on how this learning will work. So in terms of the training data, we have some existing instances of problems. So here I'm showing on the slide is a class of problem we'll consider. So it's a path planning problem. So there's obstacles, and I want to go from A to B, and then to avoid obstacles, but I still want to minimize the length of the path I travel. And we can generate a bunch of those instances from either existing problems we solve or from some generator. And then, so there, given such a collection of instances, we can transform them into, in this case, integer programs. And so integer programs here, I'm writing this in this very generic form so integer linear program, because the objective is linear and the constraints are linear as well. And so once we have the integer program, we apply within this framework the branch and bound process, which on a high level is a tree search process. We're navigating this combinatorial space of the solutions via the tree structure. and trying to find where the optimal solution is. And so once we have compiled into this problem structure, then we design some methods to generate the training data, and then learn some model that makes a decision within this framework. And finally, once we have learned such a model, then we can apply to the new testing instances generated from the same distribution where the training instances come from. And then we can test the performance of the learned model. So this is a very, very abstract level. There's a lot of components in terms of what we can learn. And that's the next point I'm going to get into. So for this class of problems, we'll consider integer programs, and the main method or the main framework people use to solve integer programs are branch and bound. So it's a complete search algorithm for integer programs, meaning that if I run till the end, then I'm guaranteed to find the optimal solution, and I'm also guaranteed to find the certificate of the optimality. So meaning I can certify the solution, the optimal solution found is indeed optimal. So it's very nice, the framework and the completeness, but the disadvantage of that is, in general, solving integer programs takes exponential time. So it's falls into the class of problem anti-hard problems. So completeness comes at the price of exponential search time. So people in practice will want to speed up the process. So sometimes we might like sacrifice the completeness with the speed by designing hand heuristics to guide the search. And we want to prioritize searching places where we're likely to find optimal or near optimal solutions. So as you can see, in the context of doing the tree search, it's about prioritizing which branch of the tree we want to navigate and which subtree we want to focus the search time on. So existing solvers, and there are a few of them that's widely used in commercial applications. What they tend to do is there's a lot of operation research experts spend decades handcrafting those heuristics to speed up the process of finding the solution. So our task from the data-driven perspective is, can we learn such a heuristic? And in this context, we're learning this node selection model. So this is given us a list of open nodes in the search tree, which node I should investigate next in order to find the good solutions. And here, as you can see, the objective is we're not aiming to find the optimal solution, because as a caveat of those heuristics, we might need to sacrifice optimality to trade off for speed for high quality solutions. So there are existing methods of using data-driven approach to learning this node selection policy. So one class of methods is based on reinforcement learning. But in this particular application, reinforcement learning is likely to be unsuccessful because of the two reasons I showed here. So firstly, we have an exponential search space. The tree, as I mentioned, can grow exponentially. So that's it's exponential in terms of the number of integer variables. And also we might face the sparse rewards problem, meaning that we might need to make a long sequence of decisions about assigning integer variables until we find a feasible solution. And then we can only then can we get the feedback in terms of how good the objective we find is. And reinforcement learning is notoriously sample inefficient in the sparse reward domain. And the second, which is more practical line of research represented here, is by imitation learning. So the existing work by He et al. Requires access to optimal solutions. So think of this optimal solutions as a way to generate demonstrations. And As I mentioned, the integer programs in general are hard and takes exponential time, the worst case to solve. So generally such demonstrations are computationally very expensive, especially for large problems. And also in their work, their generalization is limited by problem size, meaning that if I train on problems with 100 integer variables, I can only test such a model on integer programs 100 variables. In practice, though, sometimes we might really want to solve problems with, say, 200 integer variables. But because of the time budget, we can only generate demonstration for 100 integer variables. So how to scale up in terms of learning process is also an interesting open problem, which we provide one solution in our work. So pictorially, like just to motivate what's the retrospective imitation, which is the algorithm we propose, tend to aim to address those two shortcomings of those two class of methods is here. So on the x-axis, I'm representing the number of integer variables. It's growing, so think of it, the problem becomes harder and harder as more integer variables are added to this problem. And the y-axis is this notion of how difficult is it to learn. So RL, because it suffers from this explosive combinatorial search space and the sparse reward problem, so the learning difficulty skyrocket once we increase the number of integer variables. While imitation learning can more gracefully deal with increasing the size and difficulty of the problem, but it's limited in size. So that there's a certain size we can collect optimal solutions for, and that's where we draw the line of where we can apply existing imitation learning algorithms for. So for retrospective imitation, what we to compare the improvement over reinforcement is, so we densify the reward signal. So instead of only get a very sparse positive feedback in long time horizon, we aim to make this reward more dense so that we can provide more feedback in terms of the decisions we have made, so that we can effectively address the issue with the difficulty of the sparse reward in reinforcement. Compared with imitation learning, we show that there's a very simple and straightforward way to iteratively apply the retrospective imitation learning algorithm so that we can scale up to problem sizes where we have existing demonstrations. And sometimes the scale up can be substantial in terms of what the base size where we have demonstration and the eventual size where we can test the learning algorithms on. So here I'm just going to present what the retrospective imitation, what the main idea behind retrospective imitation learning is. So imagine I have some existing policy, pi1, and we roll out the policy. Basically meaning I apply the existing the node selection policy in this branch and bound framework and generate some search tree. And here, let me assume this red node with a star, that's the best solution we found by pi1. And pi1 initially might not be a very good policy, so the search tree can be pretty large. So then, once I have such a search tree, I will generate what we call the retrospective oracle feedback. So what was retrospective oracle feedback? So basically, this is given I know this solution, that's the best solution I find, potentially after a long search time. Looking back, what's the best thing I could do in retrospect? Because this is a search problem, the smallest amount of search I need to do is by following this path of red nodes, going directly from the root down this path to this red node, without making any of the unnecessary branches to the other white branches of subtrees. So this is the absolute best I could do in retrospect, and that's where the name retrospective oracle comes. Okay, so now we have the feedback. Then goes to the next step. How can we formulate this feedback as training data to update the current policy. Well, so the feedback, I know the red nodes are the absolute best I could do. Then essentially, I should really prefer to make decisions along this path compared with the decisions I actually make, like in terms of deviation to the other branches. So you can think of the feedback here are pairs of nodes because I'm learning the node selection. So for any pair of the red versus the white nodes, I should really prefer the red nodes. So essentially, the training data comes down to this pairs of the red and the white nodes along this trajectory. And the feedback is I prefer the red nodes to the white nodes. And in practice, those pairs of data gets fit into a ranking model. So essentially where the node selection policy is materialized as a ranking model. So given pair of nodes, tell me which node I should select as my final node to explore next. Okay, so this is the first iteration of this retrospective oracle. And then once we train the node selection policy using the data we generated, then we have a Pi2. And then we can repeat this process. So Pi2 might have improved a little bit. So we have a smaller search tree. And we find this solution faster using this new policy. And then we can repeat, but it's still not optimal. So we're still making those unnecessary branches and the exploration to other subtrees. So we can repeat the process of identifying the retrospective oracle and generate a new batch of data to feed into this ranking model we train to update again this policy. And we can continue until either we have met some time budget or the policy is covered. Okay, so that's the algorithm. And really, we want to understand what kind of guarantee this algorithm can give us in terms of so in this context, we really wonder how long it takes us to reach this optimal solution, given some information about the policy. So here I'm presenting a simplified version of the search process by limiting what the action space is. So here I'm just pictorially, if I'm at this blue node, I'm simplified the action space to have two such actions. So one is branch to a child node of this blue node. And the second is backtrack to the parent node of this node. And so, yeah, so those are the simplified action space. Why I call it simplified? Because in actual branch and bound, the action space is more complicated. Because in the actual branch and bound search tree, I can jump around. So instead of I only limit myself to these two actions, I could potentially jump from this red node to this left node here. But that makes the analysis very complicated, almost impossible. So that's why I stick with this more simplified action space to do that process. So given under this simplified analysis, a simplified action space, I can prove this theorem, which really analyzes the number of steps and you should take to the optimal solution. So the statement here is n represent the number of minimal steps to the optimal solution. So here I show you can think of that's the length of this retrospective optimal path. And in this one, so the n is 5. So I need at least 5 steps in order to reach where the optimal solution is. And the epsilon, that's the quality of the policy. So that's kind of the error rate of the policy with respect to the retrospective oracle. So in practice, what this epsilon is basically the training error we get from training this ranking model. So the ranking model is a binary. If you think about the final prediction is a binary, either 0 or 1. I prefer the first one and prefer the second one. And so here the epsilon is a binary classification error with respect to the retrospective oracle. Then given those two statistics, then I can make the claim that expected number of steps to the optimal solution is n divided by 1 minus 2 times epsilon. And here, notice the epsilon needs to be at most half to make this bound meaningful. And also, I should point out here, this bound is in expectation. So I mentioned before, the worst case for general integer program are exponential. So so this really tells us that there's a very long tail in terms of the distribution, but the expectation is linear in terms of n, which normally corresponds to the number of integer variables in the problem. So here I'm just going to give a quick summary of what the proof involves. It's actually pretty simple once we find the correct abstraction of the problem. So really here the observation is once we make a mistake, so what's a mistake? Well, so in this case, if I'm currently at the boot node, if I go to the left child of the boot node, then under the action space, I'm moving away, further away from where the target is. So even though we're operating in this tree search domain, we can really visualize this in this number line. So at the beginning, the root node, so I'm at 0, the starting point. In the end, that's in the assumption, that's the minimal number of steps to the optimal solution. So that's the distance I need to go to reach the optimal solution. And then in this context of translating to the number line, once I make a mistake, really I'm making a step to the left. So I'm getting further away, one step away from the optimal solution, the target location n. And since I make an assumption that I'll make this mistake with probability epsilon. So really this boils down with probability epsilon will take a step to the left. And here the making the right decision corresponds getting closer to the target. And here we make such a decision with probability 1 minus epsilon. Okay, so this is the abstraction of how we translate from the tree, navigating on the tree, to navigating our number line. And so once we have this abstraction, then we can really resort to this classical problem. So this is basically boils down this classic problem in random walks. With probability epsilon, we go to the left, and with probability 1 minus epsilon, we go to the right. And since epsilon is at most half, so we know we have a higher probability of going to the right than going to the left. And then we can use tools in this probabilities called analyzing the hitting type. Basically, I start at 0, and I want to hit the location n with the probability models I just described of moving left versus moving right. And this classical result tells me the expectation, the number of steps I need to make is n over 1 minus steps. So that concludes the proof. Are there any questions on what the proof involves?
I might ask a couple of questions that I think might help the students. The first question is this epsilon. Just so maybe you can elaborate a little bit on this epsilon. This is something that can be measured using a standard package like PyTorch or TensorFlow, right?
Yeah. So yes, exactly. So epsilon here in practice, that's the classification error from the ranking model, which the ranking model represents the no-search faults. So yeah, so this can be empirically measured in terms of the error rate.
And the other question that I think can help students a lot is this: there's nothing in this proof that requires that the errors be independent, right?
Well, that's a good question. That's actually required in terms of to invoke this result. Well, yes, yes, this result needs the error to be IID.
Okay.
Yeah, that's
okay. Can you imagine a scenario where that is not required?
Um, I'm not too sure. There might be a way to translate this non-IID, but if it's non-IID, then in order to make similar kinds of analysis, then we need to still place some structure what the non-IID is. There's still, if there are correlations, then we need to know what the correlations are.
Okay. Okay. So maybe just to summarize for the students, you have this expensive solver that ran for a long time, and it found the optimal solution, but it also found a bunch of dead ends. And all the local decisions of this that this expensive solver took is being converted into training data for this policy to make better local decisions. And this epsilon is basically the one-step classification error on those local decisions that didn't get translated into this result on the search time.
Yeah.
Okay.
All right. So as I mentioned, the second point I want to address with this algorithm is this scale up issue. Which is a very practical issue in terms of our objective is we have some solved instances, either a potential optimality of the size S1, but I'm really interested in learning policy that can solve instances of size S2, which is larger than S1. And because of which we cannot really gather any existing solutions for. And the retrospective imitation provides a very simple way to scale up. So we can just start with apply the previous algorithm with on the size of S1, where we have solutions for to train initial policy. And then what we iteratively scale up the size, so one by one. So we can train this, given the new size, by running this the policy trained on the previous size to generate initial search trees. And here we're banking on this implicit assumption that if we don't increase the size too much, then the instances will not look too different, which means the policy trained on the previous size can still work, generalize pretty well on the slightly larger instances. And then once we generate the initial search tree, then we can apply the recursive imitation learning algorithm to identify the mistakes and package those into the training data and train the new policy that works on this larger size. So one question is, okay, this sounds like a sensible way to scale up, but can we say anything theoretical? Because really here we're doing this transfer learning where the initial training distribution and the final testing distribution have this gap in terms of the size. So here we introduce this assumption called trace inclusion. So what this means is, so on the high level, we assume this rollout trace generated by a policy contains the trace from the expert. So imagine the tree on the right is generated by our policy. And within this policy, the one I circled inside is a tree generated by the expert. So expert here can mean a solver or some other learning-based methods applied to branch and bound. So really this assumption is one way to interpret this assumption is the policy we have is actually in a sense like spends longer to find where the optimal solution is. So why I make this kind of similarly strange assumption? So this is like because I want to make the claim, but I explain like what's in practice, what's the implication of this. So the theorem we can claim is from scaling up, so from S1 to S2, with S2 larger than S1. If we make the trace inclusion assumption, then the error rate, so remember the error rate, the previous theorem depends on, trained via retrospective imitation will be lower than that trained from direct imitation learning. So the imitation is from the expert. So why this is the case? Well, So really here, where the power of the trace inclusion probably comes from. So imagine the feedback we get in terms of the ranking pair for the recursive imitation. Because the search tree we generate is larger, so we're going to collect more feedback than just collecting feedback from the subset of the search tree where the expert can provide. So in particular, it's a strict superset of the feedback we can get from imitation learning. And so that's why we can get more feedback on where the mistakes are. So that's why we can obtain a smaller error rate. And in practice, what this means is a lot of the solvers are very effective, meaning they can generate extremely small search tree on small scale problems. And for a policy that's initially that's not very good, this actually it's likely to be satisfied. Meaning that, imagine if there is ideal this retrospect oracle exists as a solver, then it will go directly down this path. So that will be automatically be included in any search tree we generate. It will be a subset of any search tree we generate. So that's the connection between the theoretical claim and the practical the practical aspect of the claim. And under this claim, we can really guarantee the sizes, like the scaling up, we can maintain this low error rate property as an algorithm. And what this low error rate implies from the previous result is we can expect in expectation the search time will be shorter for the retrospective imitation learning policy versus the imitation learning policy. So so next I'll go through some experiments validating the effectiveness of the retrospective imitation learning algorithm. So the first one is A-stars applied to A-star search for maze. So on the right here is the example of the maze. We want to go from the top left to the lower right. And here in this picture, I'm showing here the red path. That's the shortest path. Go from the start to the end. And the yellow squares are, so in A-star, it's again a tree search structure. I'm building this the search tree in order to find where the exit is. And the yellow square basically it corresponds to the square that's nodes of the tree where the algorithm explore. And how does A-star build this tree is by this heuristic function to guide where the search goes. And so we want to validate the scale up. So we scale up from the mail size from 11 by 11 to 31 by 31, meaning that we'll run existing A-star with Manhattan heuristic to generate where the shortest path is on only the smaller size. But in the end, we want to train a policy that works on the large size. And so we provide some comparison with first existing imitation learning algorithm. Right? So the recursive imitation is a meta framework that can be combined with any existing imitation learning algorithm. Here, in which case we combine that with Dagger data set aggregation algorithm. And on x-axis is the maze size. We go from 11 by 11 to 31 by 31. And the y-axis is the number of squares. So think of that's like the size of the search tree. So that's why we want the smaller, the better. And here, as you can see, the blue line, which is a retrospective imitation, is it's able to obtain a much smaller the size of the search tree compared with both Dagger extrapolation and Dagger cheating. So what Dagger cheating is at each scale. So remember, for retrospective imitation, I only have demonstration on the smallest scale. I don't have any other demonstrations on the larger scale. So for Dagger cheating, I provide demonstration on each scale. So it has a lot more training data than what retrospective imitation learning has. But it still has a higher number of squares. So this validates in terms of the error rate. Actually, in the paper, we do have the error rate comparison. So this is an indication of the error rate for retrospective imitation is lower than the dagger cheating. So just directly apply imitation. Dagger extrapolation, well, so we control the same amount of training data. So the dagger only has demonstration on a smaller scale. And then on the larger scale, we'll directly apply the train policy on the small scale. So here the issue is generalization, because the shift in the distribution from the size, the dagger extrapolation, the size of the x squares just gets blow up. And also compare with existing A-star heuristic, like because we're learning this new heuristic in the form of node selection, want to see how effective it is compared with A-star itself. So here, A-star is using the Manhattan heuristic, which is a very canonical heuristic to use. So we're able to obtain a lower number of squares, which means we can outperform the manual design Manhattan heuristic. By the way, also we here include the RL, which, as you can see, perform much worse. So this is demonstrating this long search horizon and the sparse reward problem, because I need to generate a potentially large tree in order to locate where the exit is. So RL is very ineffective in this domain. And for the practice, that's kind of the toy example. So for practical, we do experiments on this risk-aware path planning. And so here we're scaling up from 400 integer variables to 560 integer variables. And again, compare with imitation learning. So here I only show the dagger extrapolation. We consistently here on the x-axis is scaling the problem size. The y-axis is optimality gap. So how far away from the optimal solution is. So here lower is better. And the retrospective imitation learning is consistently can get to 0 or near 0 optimality gap when we scale up, while just not able to extrapolate the base policy learned on the base scale doesn't work. Compare with existing solvers, we can also outperform. So here we compare with two solvers, Groupie, which is a state-of-art commercial solver, and the Skep, which is a state-of-art open source solver. And again, so in terms of comparing the optimality gap, we can get much lower optimality gap within the same budget in terms of if we control the search tree size. So here we're budget 2K. So given we only export 2,000 nodes, we can obtain a much lower optimality gap compared with the existing solvers. So this is an indication the data-driven approach we employ is able to learn a much effective node selection policy compared with manually designed heuristics. Okay, so that concludes the first part. Any questions on this part? Okay, I think I'm kind of running short on time, so I'll go through the second part quickly. So the second is on this co-training. So in the previous one, we're mostly focused on imitation learning. But the second one, we're showing is a very general that can unify different learning paradigms, either reinforced learning or imitation learning, to combine them to do this policy learning. And this is joint work with Ravi, Isong, and Hiro. So here really the motivation of this approach is different representations of problems. So for example, here I'm showing this combinatorial optimization over graphs. So specifically minimal vertex covered problem. So naturally it has a graph representation because it's defined over graphs. But also we can write this as an integer program. By solving this integer program, the optimal solution corresponds to the optimal solution, the subset of the minimal vertex cover. And the scenario also applies for the path planning in terms of how we want to characterize what the obstacle looks like. And so here really is the main idea. We're like really inspired by this co-training idea. So they're combining two different frequency representations to train a better classifier. So here is the example is if I want to train a classification for an academic website or not. And so here, what what two class of features we have is firstly the hyperlinks. We have it on our website. So for example, they'll say Professor Blum and my advisor. So those are good indications this might be an academic website. And the second representation as the actual text on this website. So they might have words like university, publication, conferences, which are another indication of this is an academic website. So really the code training algorithm proposed by Blum and Mitchell is how to combine those representations to do a better classifier than simply concatenate those two features. And really the algorithm is quite simple and I think it's really elegant. So what they do is they have a set of labeled examples and a set of unlabeled examples. So the first, what they do is they train a classifier on the labeled examples using the first feature representation, and train a second one using a second representation. And then they use the first classifier to label some of the unlabeled examples. So here I only label the most confident labels the classifier 1 has, and do the same thing for classifier number 2. So after doing this, I get more labeled instances where the new labels is generated from the existing classifiers. So then we can add those to the existing labeled examples and then retrain the classifiers and repeat the process. And so this is a very simple algorithm, turns out to be extremely useful for classification. And so here in this work, we generalize this for policy learning. So we're making a sequence of decisions. So the core of the algorithm here is, so here I'm showing this in this very poor example of doing the middle vertex cover. So first I'll write down those in terms of 2 representations. And then I can train on each representation a policy. So here on representation A, I'll train a pi A. On representation B, I'll train a pi B. And so in terms of the training, how the training is done, so that's very flexible. So that's where we can either use reinforcement learning or we can use imitation learning. So we don't really care. The algorithm doesn't really care what algorithm is used. So once those 2 policies gets trained, then they can produce solutions on those problems. So here I'm labeling, so the middle vertex cover, the vertex cover generated by pi A, so 1, 3, 4, 5. So as you can see, this is not the optimal one. Versus pi B, the solution generated by pi B is actually the optimal one. So here, x2, x3, and x4 assign value 1. So basically that's the value. So that's like, if it's like 2, 3, 4, so that's one of the optimal set of the minimal vertex cover. So once I know, because they are solving the same problem, essentially just using different representation, so then we can compare the solution quality of the final solution generated by those 2 policies. And in this case, pi B has a better solution than pi A. So then we can provide the solution by pi B as a demonstration to pi A. And additionally add this imitation learning loss to whatever loss is associated with training pi A as an additional loss function to retrain pi A. So this is basically the algorithm. Again, the question we're interested, can we say anything theoretical? And why likely this kind of algorithm is likely to work? So essentially, what different representation capture is the different difficulties for policy learning. So if we visualize all the class of problems, like say all the middle vertex cover problem, that's the set B. So if we consider the difficulty for using the first representation versus the difficulty of solving using the second representation, then we have this division of subset. In D1, where representation A is easier to solve, and D2, representation B is easier to solve. And then in practice, we can really quantify this in terms of how much the gap is, like how difficult or how much easier a class of representation is compared with the other. So here, delta 1 and delta 2, kind of like delta 1 is the, so eta here, I can think of is the objective. So delta 1 is the advantage of representation A over representation B on the distribution D1. and delta 2, that's the opposite. And we also formulate this in terms of the policy difference. So we have two policies, and we really want to know how different those two policies behave in terms of in how they generate the final solutions. And those beta terms are based on this Jason-Shannon divergence, and there's a way to quantify the difference. So really the theoretical claim we can make is about this policy improvement. So by training the policy, so here the J is the policy quality. So the higher is better. And so here the term, if you look at the bound, what the term is here is involving the trade-off between the beta term and the delta term. So epsilon here is some fixed quantity associated with the policy. So it doesn't really matter in terms of distribution of the problems. So beta here is policy difference, and it's minus. So in order to maximize this term, I really want to minimize beta. So I want to make sure the two policy behave similarly, even though they're operating using different information on the representations. While the delta 2 here is positive, so I really want to maximize this term. So because this means that I really want the difference, difference in difficulty on the two representations to be large, so that I can really take advantage of the difference in difficulty to give me a higher improvement bound on this policy learning system. And so that's essentially what the algorithm is doing, where the imitation learning part is trying to make this two policies similar in terms of the solution they produce. And then we're squishing out this term in beta here. And so for experiment, we do this for the minimum vertex cover and the Rick square path planning. So here, really, we show a comparison of doing the code training. So one thing about code training is, so there are three classes of comparison I will draw your attention to. So firstly is doing baseline where there's no code training. So we just directly only take one representation and do whatever learning we want on the representation. So here, the x-axis is the problem size, and the y-axis is the performance gap of with CoPier. So here, lower is better. So compared with those baselines, either using RL. So here on the graph representation, we use RL, and on the integer program side, we use imitation learning. So by doing code training, we can improve beyond those just a single representation baseline. And also one nice result of doing code training is in the end, I have two policies based on each based on one representation each. So at test time, what I can do is I can, given a new instance, I can run both policies on those two representations and generate two solutions. And I just return whichever solution is the best. So that's what we call the CoPier final. So that takes the better one of the two poles. And as a matter of fact, by taking this very simple enhancement, we can improve the policy a lot. So here is just those two bars are just return compare the after doing code training, but only look at the solution produced by a single policy. By combining the policy, we can reduce the gap a lot. What does this imply? So this implies that by doing the code training, there's actually a very explicit split in the difficulty of the problem. So some problems are much easier in one representation, and some are easier in the other. So by taking the better of the two, we can really harvest the difficulty in the learning difficulty and get a solution that's much better. And finally, compare with a strong existing solver, such as Groupie, the code training final approach is again much better. And we see the similar results on the risk square pattern. Okay, so that concludes the second part. Any questions on this part?
So maybe I'll lead with a few questions. Are there cases where you don't get a clean one-to-one translation of solutions from one view to another view, like perhaps there's a one-to-many or it's not an exact translation?
So for the problems we consider so far, that's not the case. But there are cases, I think, in terms of partial solutions. So if I want to extend this in terms of so here, like the algorithm needs to wait until it produces the final solutions in order to proceed with this co-training procedure. So sometimes that can, for example, integer program that can take long. So then really we want to ask, can we do this like in the middle? Like if I have a partial solution, can we translate? So I think for some instances, for example, integer program, um, that might not be very straightforward. Like for example, if I look at the minimal vertex cover case, the partial solution on the graph side is like the subset of the nodes that selects this above. That corresponds to, there's a naive way to translate to the partial solution into the program side, but that doesn't give me, because it's not a final solution, so then it's hard to collect the feedback I get, because there's some issue with like, say like the branching order. Maybe I haven't even branched on this node yet in the branching bound framework. So I think that's where the issue described might happen. In terms of mapping one to many, it's not immediately clear where such a case will happen.
Maybe another question is, what do you think will happen both in terms of the algorithm and empirical performance and in terms of the theoretical analyses if one were to extend to more than 2 views, like 3 or 4 or 5 views?
Yeah, that's kind of like what I want to talk about in the future direction section. So I think the short answer is if there are more than 2 views, there's a naive way. We can just generalize. We just run this for multiple views and then provide the best solution to the other views. But this is likely losing information because we're only effectively using a solution of only one view. So there might be some other ways, like based on this kind of like this triplet learning kind of paradigm to generalize to multiple views. And in terms of theoretical, but I think theoretically, even the naive one, we can maintain the theoretical guarantee. But the question is that the best we can do? Which I don't think that's the case.
Any other questions?
Okay, so just going to summarize what I presented so far and some future directions that might be interesting. So for the first work, to learn to search via retrospective imitation, we apply this idea of learning by identifying and correcting mistakes and provide theoretical characterization of this learning algorithm. So the future direction, I think one obvious question is, can we generalize this beyond tree search? Because like how the retrospective oracle is designed currently relies a lot on the tree structure in order to find these shortest path. So actually there are existing work that kind of uses like idea of identifying what's the best in retrospect or in hindsight. But those are, I think they are similar, but not quite what we want in the sense that there are different procedures, I think, in identifying the mistakes on this learning process that can generate beyond tree search. And the second one is co-training, so combining multiple representations. So yeah, ESON patchbound is generally designed beyond 2 representations. So like I think you get the idea from this more like a multi-view learning or the triplet loss-based learning. They might provide some interesting directions. And another thing I want to point out is co-training when they are not actually explicit. That's like the other direction, the beyond 2 representation. So what if there's only really one representation and there's no obvious second representation? So here I think we can really turn really what the theory really says, what the algorithm really says. The having two representation is nice, but it's not like absolutely necessary. So if there, we can think of applying this different learning procedure. Even for example, even if I only have one feature representation, but I do reinforcement learning versus imitation learning. So they will result in different policies. So once I have two different policies, then we can really commence what we do in this co-training procedure. So I think there's a interesting question in terms of generating this idea, like drop this requirement for different representations for more thinking about the algorithmic level. How is there a version of code training not contingent on representation, but contingent on different algorithms? So I think that's the future directions, I think, for this code training idea, either going beyond to more representations or going to the other whole class of point of view of on the algorithm side, how to do code training with different algorithms. That can be interesting future directions. Yeah, so that's all. Any questions?
Any questions? Okay, thanks, Jialin. And tune in on Thursday. We have a guest speaker on Thursday, Jennifer Lustgarten from UC Berkeley will be giving a presentation on Thursday. Thanks, everyone.